Hello, my name is Maria Katsikini. I'm professor at the School of Physics of the Aristotle University of Thessaloniki in Greece. And I'm going to present a case study on the use of X-ray fluorescence mapping and X-ray absorption fine structure spectroscopy for the investigation of the spatial distribution and stability of nanoparticles injected in tissues. Why studying nanoparticles? Because they are used in therapeutics and diagnostics. These two terms are combined in the new term theranostics. I'm going to present applications of gadolinium, europium vanadate nanoparticles, and they are attractive because they are suitable for multiple bioimaging modalities. For example, europium exhibits strong luminescence in the red part of the visible spectrum, and it is suitable for fluorescence imaging, whereas gadolinium, with 7 unpaired electrons, has attractive magnetic properties, and it is used in magnetic resonance imaging in MRI. Other applications are for nanosensors for reactive oxygen species, which are involved in inflammation, as probes for local temperature measurements with micrometer spatial resolution, for improved local efficiency of cancer radiotherapy, and for drug delivery. Now, why is it necessary to study by imaging the nanoparticles after injection into tissues? Nanoparticles for biomedical applications are either induced intravenously, injected intravenously, or they are directly injected in tissues or tumors, etc. For example, in hyperthermia treatment of cancer, the nanoparticles are injected directly in the tumor. But the main problem is that tissues are inhomogeneous, and the transport and distribution of the nanoparticles cannot be easily predicted or modeled because there are various parameters which are involved, like the injection rate, the injection volume, the concentration of the nanofluid, possible aggregation of the nanoparticles, surface interaction with the tissue porosity, etc. Now, why using synchrotron radiation X-ray fluorescence spectroscopy for mapping? Because in this way we can simultaneously map different elements in the sample. For example, vanadium, gadolinium, and europium. And also, by combining with X-ray absorption fine structure spectroscopy, we can obtain information on the speciation, the bonding environment of the different nano elements in the nanoparticle, and also on their oxidation state. Now I'll continue with a short timeline on this study, starting from the conceptualization of the experiment. So the trip actually started when Dr. Alexandrou came to Thessaloniki, to our university, to give a talk on the biomedical applications of nanoparticles. After the talk, we had a discussion on how can we collaborate on the study of the spatial distribution of nanoparticles by means of synchrotron methods. Then we decided to submit a proposal to BESI for measurements at the KMC2 beamline. But before submitting the proposal, we had to contact the beamline scientist in order to discuss the feasibility of the measurements. In March 2019, we submitted the proposal. We asked for financial support through Calypso Plus, which was the predecessor of the NEPHEWS project. The proposal was accepted. We were informed on the beam time schedule in May. Then from summer to winter 2019, we had to discuss on which kind of tissues we are going to study and on which concentrations of the nanoparticles. We had to do the registration, the user registration at BESI to make all the travel arrangements. And The samples were express-mailed from France to Germany. They were just arrived the first day of the beam time. So after the beam time, we had to do all the reimbursement procedure for the trip with Bessie, to do some preliminary analysis of the data in order to submit the report to Bessie. Part of the data, some of the data were presented in a master thesis, also in local conferences. We continued with the analysis, with the XRF analysis, and in July 2023, we have submitted a paper for publication that was accepted finally after almost 1 year. So let's proceed with the results and the sample preparation. So the gadolinium europium vanadate nanoparticles were prepared by co-precipitation synthesis method at ambient conditions, using, of course, proper precursors. A transmission electron microscopy study revealed that the nanoparticles had an oblate shape with an average length of 40 nanometers and average width of 15 nanometers. Then the next step was to prepare the nanoparticle colloidal suspensions. The injected volume was 10 microliters of colloidal suspensions, and we have prepared 3 different solutions of 5 milliem, 10 milliem, and 30 milliem in vanadate concentration, which was determined colorimetrically. The molar concentrations of the nanoparticles were 90, 180, and 530 nano-m. Now, regarding the injection, we decided to use mouse ear pinna, the lobes of the mice ears, because they offer some advantages like small thickness, accessibility, and easy treatment. However, as in the case of other tissues, they are inhomogeneous. A light microscopy image of a histological section is shown here. This is obtained from the literature. And we observe here different layers with different structures. And this is one complication of the tissues. The in vivo injection took place immediately after euthanasia. Then the ears were cut off, they were rinsed with phosphate buffer saline, and they were stored in glass containers with 4% paraformaldehyde at 4 degrees Celsius. For the XAFS measurements and XRF measurements at synchrotron, we just wiped with absorbent paper the tissues, and we have fixed them between 2 pieces of adhesive tape. Now, regarding the techniques, as I mentioned, we have used X-ray fluorescence spectroscopy, which actually studies the energy distribution of the emitted fluorescence photons emitted after the sample excitation with monochromatic X-rays. This method is suitable for quantitative analysis of the samples, and it can detect elements with atomic numbers higher than 13. X-ray absorption fine structure spectroscopy is an element-specific technique. It studies the dependence of the X-ray absorption coefficient on the energy of the impinging beam. XAFS spectra can be recorded at the absorption edge of different elements like vanadium, gadolinium, or europium, and it is suitable for the determination of the bonding environment and the oxidation state of those elements. In our case, we have used a capillary in order to reduce the beam size to 5 micrometers. That is suitable to perform X-ray fluorescence mapping. All the measurements were done at ambient conditions, which means that high vacuum is not necessary at this energy region. A top view of part of the beam line is shown here in this photograph. In this pipe, the X-rays are propagating. This is the experimental hatch. Of course, during the measurements, the doors are closed in order to protect the users from the radiation. A closer view of the stage is shown here. This is the fluorescence detector, the sample is positioned here, and there's a number of motors, piezoelectric motors, in order to move precisely the sample in various directions and rotate the sample. An even closer view is shown here. This is the capillary, the sample, and the detector. The detector and the capillary, of course, are located on the horizontal plane, and the angle between the capillary and the sample surface is 45 degrees. Now, there are different ways, different acquisition modes for the X-ray absorption fine structure spectra. And the most common way is the transmission mode, where the sample is positioned between two detectors, ionization chambers. One counts the intensity of the impinging beam, and the other one counts the intensity of the transmitted beam. Then the law of Beer-Lambert can be used in order to determine the energy dependence of the X-ray absorption coefficient. This X-ray absorption coefficient is proportional to the number of the core holes created due to the absorption procedure, due to the photoelectric effect. This acquisition mode is suitable when we have homogeneous samples, thick samples, thin samples, etc. Another method, which is more suitable for diluted samples, is the fluorescence yield mode. In this case, we need a fluorescence detector which counts the number of the emitted fluorescence photons, because this number is proportional to the number of the core holes created, which is proportional to the absorption coefficient. In this case, the sample is positioned here. As we saw in the photograph, we can use a focusing element in order to reduce the beam size, and we need a fluorescence detector. The advantage of the fluorescence yield mode is that it can be very well combined with X-ray fluorescence spectroscopy, because with the same setup, the same detector, we can both record XAFS spectra and XRF spectra and XRF maps. Now, I will continue with some spectra. This is the XRF spectrum of the gadolinium europium vanadate nanoparticles injected in the tissues, and we observe a number of peaks. This peak here, the most intense, is due to elastic Rayleigh and inelastic Compton scattering, and the other peaks are emission lines due to fluorescence. In the case of vanadium, we observe two K peaks, K emission lines, K alpha and K beta, whereas for europium and gadolinium, we have more peaks that originate from L emission. Now, in order to obtain information on the content of the elements, we should feed the spectra. In this case, for this purpose, we have used the PYMCA software, and there is a very simple formula that relates the area under the peak with the concentration of the element. However, we need to know a number of parameters which are actually probabilities. Probability for absorption of a photon, probability of the excitation by means of fluorescence photons, and probability for emission of a specific line relative to the whole series. Now, a much easier way is to determine method is the determination of the ratio of the concentrations of two different elements, because by dividing this formula written for two different elements, we can get rid of some factors of this formula. So by directly taking the ratio between the area under two peaks and correcting for the sensitivity factor, we can determine the ratio of two elements in a sample. In our case, the ratio of europium to gadolinium was found equal to 0.64, and if we assume a formula like this, chemical formula like this, X is equal to 0.61, which is the nominal value. So we verify the composition, the molar concentration. Now, in order to do XRF mapping, we have to do two things. The first thing is to set regions of interest, the so-called ROIs, which are actually energy windows that separate the contribution, the fluorescence emission of the different elements present in the sample. And the second thing is that we should micrometrically move the sample, raster scan the sample in order to construct the XRF maps. So the first map is shown here. The injection here was done with a high concentration of gadolinium europium vanadate nanoparticles. The big map was recorded with a step of 25 microns, whereas a small, more detailed map of this region shown in the inset was recorded with a step of 5 microns. We observe here that the nanoparticles follow paths of easy flow, and they are not homogeneously distributed in, let's say, circular or a tear-shaped area. Now, another piece of information we can obtain is to check if the elements are co-localized. So we have prepared maps, color maps, red for vanadium, green for gadolinium, and blue for europium. And then we superimposed these maps with certain transparency. And according to the RGB model, when we observe white parts, this means that the elements are co-localized. So this is the case here. So we don't have out diffusion of gadolinium, which is toxic in the tissue. It remains in the nanoparticle. An additional method to test this is to prepare correlation graphs where we have the intensity of gadolinium versus the intensity of vanadium or europium. Each data point here in this graph corresponds to one point in this map. We observe here a very good linear correlation with correlation factors higher than 0.98, which means this is an additional indication that gadolinium, vanadium, and europium are co-localized. This means that the integrity of the nanoparticles is preserved and we don't have out diffusion of toxic elements. Another map is shown here, and a third one here. This one corresponds to the lowest concentration of the nanoparticles. And in this case, we observe an extended area rich in nanoparticles, which is most probably the injection site. And this broad distribution bifurcates to thinner channels or regions with lower nanoparticle content. So again, we verify that the nanoparticle colloidal suspension follows paths of easy flow. Now let's continue with the XAFS spectra. In our case, in order to record the XAFS spectra, due to the low nanoparticle concentration, the low flux of the beamline at the vanadium KS, and the acquisition of the L3 edges for europium and gadolinium, which means that we had a lower fluorescence yield. It was not the quality of the spectra using the capillary was not very good, so we removed the capillary and we did the acquisition with a broader beam of 0.6 to 1 millimeter. We have also used the ROIs in this case in order to isolate the signal from vanadium, europium, gadolinium, and get rid of the background due to preceding edges. So the XAFS spectrum is shown here, and this spectrum is divided in two parts. The part which is close to the absorption edge, and it is called XANES or NEPHEWS. It is the near edge structure. In this case, the outgoing photoelectron has low kinetic energy and it is shortly trapped to empty states like antibonding molecular orbitals or atomic states. Whereas the part of the spectrum that extends up to 1000 eV above the absorption edge is called XRFs. It is the extended part, and it has a characteristic oscillatory behavior, which is due to interference effects between the outgoing photoelectron wave and the waves which are backscattered to the neighboring atoms. Now, let's start the discussion with XANES spectra at the vanadium K edge, and this spectrum is the spectrum that corresponds to the nanoparticles. In order to obtain information on the oxidation state, we usually use this pre-edge feature, which is called a pre-edge peak. This pre-edge peak is observed in the case of transition metals, transition elements, when they are bonded with oxygen, nitrogen, etc. The pre-edge peak is due to 1s to 3d transitions, which are actually not allowed in the dipole approximation, but it becomes allowed with due to hybridization of the 3D with the 4p states upon bonding with oxygen. In the case of a non-heterosymmetric environment of vanadium, like a tetrahedron, as it is shown here, this pre-edge peak gains intensity. The intensity and the position of the pre-edge peak can be used in order to determine the oxidation state. In our case, we compared the spectra of the nanoparticles with vanadium K edge spectra of vanadium oxides and with sodium vanadate. So we observe that from the position of the pre-edge peak and the intensity, we can deduce that vanadium remains in vanadate and the oxidation state is 5+. Now we proceed with the europium and gadolinium LH XANES spectra. In this case, we observe one actually intense peak, which is called white line. And the position of this peak, of the white line, is a fingerprint of the oxidation state of europium. Why is that? The measurements here are done at the L3 edge, which means that the initial state of the electron is a 2p, and the final state is 5d or 6s. However, if the oxidation state changes, this means that electrons are removed from the outer cells, and this reduces the screen of the electronic cloud and affects the energy position of the initial state. So, by directly determining the position of this white line, we can deduce if europium is 3+, 2+, or if we have coexistence of these two oxidation states. In our case, europium was in 3+ oxidation state. Now, XRF spectra, in order to obtain information, structural information, we have to subtract the atomic background, continuous background here, and convert from the energy space to the K space to the photoelectron wave number. So in this way, we isolate the XRF oscillations. If we Fourier transform, we go from the K space to the real space. R is here in the horizontal axis, and this is a so-called pseudoradial distribution function, which shows each peak corresponds to nearest neighboring cell. So this is a convenient way to present the XRF data. In order to obtain structural information, we have to fit the H of K spectra as a sum of sinusoidal functions. Each function corresponds to a different nearest neighboring cell. Some of the parameters which appear in this equation should be calculated with a proper software, PHEF in our case. This is the backscattering amplitude, the phase difference due to scattering by the neighboring atom, the photoelectron mean free path, whereas other parameters like the nearest neighbor distance, the coordination number, and the Debye-Waller factor, which accounts for the static and thermal disorder, are obtained by the fitting. So let's compare the spectra prior and after the injection. The Xane spectra at the vanadium K edge, europium L3 edge, and gadolinium L3 edge, and the XRF spectra at the gadolinium and europium L3 edge, K space, R space. Nanoparticles before, prior to the injection, after the injection, here also prior to the injection, after the injection. And in the case of XRFs, black lines correspond to the experimental data, whereas color lines correspond to the fitting. So we can directly observe that there are no differences in the spectra prior and after the injection, which means that the bonding configuration of the elements is preserved. They are not dissolved. Now, the fitting results of the XRF spectra for the gadolinium L3 edge and the europium L3 edge. Nanoparticles prior to injection and after the injection, we observe that the nanoparticles have the expected structure, and that europium substitutes for gadolinium. In the case of vanadium K edge, we analyzed the spectra only prior to injection, because the spectra after the injection were of bad quality. And in this case, we verify that vanadium forms a tetrahedra, remains in the vanadate ions, and again we have the expected structure also from the vanadium point of view. Now, to conclude, XRF mapping and XAFS spectroscopy were successfully used for the study of the fate of and the distribution of gadolinium, europium, vanadate nanoparticles injected into mouse ear pinna. XRF spectroscopy verified the stoichiometry of the nanoparticles. XRF mapping revealed that vanadium, europium, and gadolinium coexist, and therefore no out-diffusion of elements from the nanoparticles to the tissues takes place. And the nanoparticles follow paths of easy flow, and bifurcated spatial distributions were observed. XAFS spectroscopy provided the speciation of gadolinium, europium, and vanadium. Europium substitutes for gadolinium in a zircon-type gadolinium vanadate structure. Vanadium remains in the vanadate ions, and variations in the element speciation did not occur prior and after the injection. Now, to close, some tips for a successful experiment. Find the proper beamline. Prepare a convincing proposal. Prepare carefully the samples. Always bring more samples in the beam time. Find the proper software for the analysis, and don't give up.